again, our ease of use here is paramount. So recovering dead hosts has got to be very easy. Adding new hardware has got to be very easy. And making use of the database, the data that comes in there from these hosts, has got to be very, very easy. So we're going to hold all of these things in the central database that Rich showed with the MoFlow graph earlier. We're going to show or store the job details, all the code coverage graphs, the test cases as they're created, successful crashes, along with all of the data that's very simple to get. And we actually store that in an XML database that is then pulled into the triage code that we'll talk about in a second. So the basic flow is pretty much like this. There's job collection, where you'll get, as a debugging host, you'll get either a file that's already been created for you or an input that's already been created for you to hand to the process, or you'll get a description of how to create that. This will be handed to your fuzzing engine, which should be interchangeable. So in our case, we pull in a DLL, and that'll tell you that DLL gets a script that tells it how to do the mutation or how to do the generation or what needs to happen, and then it'll spawn 2 threads. One is going to be the debugging test thread, which is watched with the debug extension stuff, and another is going to be a CPU monitor to decide when we're done looking at this thing. And in the case of a crash, we're going to do our data collection using our CODIS disassembly and basic Windows debug extensions. And then we're going to report that back to the database using a simple curl line. It just goes to a web interface to the database, stores it all up there, and it'll show it to you later. So what kind of data are we going to gather here? We absolutely, absolutely, absolutely must store enough data to bucket our crashes. People have talked about bucketing before. It is not an option. It is absolutely necessary. Okay? Secondarily, we need to be able to have some sort of categorization for that bug. Where did it crash? What did it look like? Is it a write violation or a read? And what does the block of code look like around it? If I have a read violation, that might not be very interesting, but it's a read violation that I'm then going into an object and pulling out a function pointer and making use of that. It's probably used after free, and I really want to know that. So I want to be able to see the whole block, not just where it crashed. And we're going to store everything that we can get. So everything that we can possibly think of to pull out that's very simple, that's on the tip of the debugger at the time, we're going to store all that in our XML. We're going to toss that into our database. Because as we said, we really have no idea what's going to be important later on. Okay? So we've got that rotating work going on, creating our fuzzing. Our second part is our completely separate team, which is the triage team. And they're going to be mining crashes out of this database that we've set up for them. Okay? They're going to decide what's relevant to them as far as targets right now, as far as their knowledge. Pick out the crashes from the database with searches, which you can separate through any of the fields that we pull. And then mine them out for going into triage. Like I mentioned before, very hard to exploit bugs are very awesome, but they're really bad ROI. We want to keep our pipeline full for as many people as we have doing exploit development, doing triage, but we want them to also have a good output. So we want to smartly pick what we're pulling out to triage. So that's kind of a tiny screenshot because we're at a horrible projector up there, but that's our basic web interface. So you can see you've got the instruction, you've got all of your registers. For any crash bucket that you have, you can pull down the XML that was set up there. You can pull down the sample, and Rich's triage code will go up there and automatically put in its search, find a set of them, pull all the XML and all the samples out, and then it can do the tracing on it. And he'll show you that right now. We got 15 minutes.
Yeah. Well, I don't have a graphical representation. Yeah, I don't have a graphical representation of the data flow analysis because at the end of the day, it's the code's going to be out there, the pinflow module that I wrote. More or less, so MPIN flow, you have several locations where you can hook. So when you need to get to the point of determining things along the lines of exploitability, triggering conditions, root cause, code coverage isn't going to cut it. You're going to need to understand a little bit more about where data specifically flowed, which instructions were operating on that, and whether or not there was a dependency chain when memory was moved from one dereference into a register and then back out into memory. So the things that we're looking for in triage is whether or not the specific bug that we found is exploitable. Now, obviously, if you're crashing on a call to a bad memory location, that's pretty safe to say it's exploitable, assuming that you have some control over that value. But if we want to determine more specifically, we have a read AV, and we need to understand which bytes of this value were interacted with by user data. Then we need to take it a little bit further. In order to do that, we will rerun, taking that XML information from Lurene's online fuzzing tool. We'll take that exception information, feed that back into the tracer, and say, okay, instead of doing an efficient code coverage trace, this time we're going to need to do some additional tracing. Going to hook every memory read-write access and log that all to a file for later analysis. That same data can be used to locate the triggering condition. Now, in our situation, in this specific case, where we're doing fuzzing, mutation fuzzing, we actually know the input. So we know that we modified this byte in this file, and it led to this crash. So in the context of fuzzing and finding new crashes, it's less important to understand the triggering condition. There are people that are doing research out there right now that you'll generate, JS FunFuzz, for example, will generate a huge JavaScript file. They implemented a BNF grammar for the JavaScript language, which means that they were able to abstract the interactions between the objects and the functions that are available in JavaScript so that they know that this function uses this type of object, and now you can mutate it all around, and anything that outputs this type of object can now be fed back into that function, etc. So at the end of the day, they end up with a 100-line JavaScript file. They have no idea what it really does, and it might lead to a crash. Some people have been developing things that, one by one, take out a line of that, rerun it, see if it still crashes, try to determine it that way. There is better ways to do it through taint analysis. And so if you were dealing with an external crash, if you have a bug that you need to triage that's as part of your vulnerability development process that somebody submitted to you, then finding the triggering condition is much more important. And so taint analysis is another part, or triggering condition analysis and can be achieved through taint analysis and is also part of the triage process. And then finally, without doing any additional work on top of that, you can also help understand root cause. If you have several bugs that are ending in the same EIP location, but have exercised different code paths, or the vice versa, where you have several different crashes, but when you overlay the graphs, you notice that, they all originate from a higher level point in the graph, then perhaps you should look a little bit closer at the interaction going on there to determine if that's actually where the bug was introduced. And then later, as that structure was accessed throughout the program, then it will crash. As far as getting the exception information, it's pretty straightforward. Brute file, again, uses some of the libcodis data to be able to disassemble the program at the location of the crash and just packages that nicely into an XML format, or can also push it into a database. And at that point, you would open back up that MoFlow visualizer and say, this crash is interesting. Let's go ahead and start working on locating the graphs that are interacting with this location where the exception occurred, and also rerun that same exact file to produce the same exact crash, hopefully, but this time with data flow. So yeah, I more or less already mentioned this, but the blocks that are hooked will also inject instruction callbacks after every read or write operation to get the data flow, and that's output into a huge log file. I mean, every single read or write instruction is recorded with the register values realized. And from there, you go through a process of building a hierarchy and dependencies. So you would actually get all the data flow from the moment that the program was loaded into the memory space. So first, you need to locate those APIs again that we're interested in, those attack surface APIs. And specifically, you're looking for the time that API was called with the file that you gave to the program to cause the crash. From there, you begin to follow this graph of dependency. and build more or less what a lot of people call shadow memory. There's a couple of ways to do it, but shadow memory is a pretty straightforward way where you're representing each byte of memory or each bit of memory in your own private copy. By doing that, every time an address is overwritten, it's determined whether or not that address had dependencies upon it, and that would be wiped out. Or if it's overwritten, then the dependencies from the source will be copied to that overwritten value. And this is stuff that we have in kind of really proof of concept stage. So this will be something that we're going to be releasing in the following months. I believe we're going to be packaging these tools separately and trying to release them one at a time so that you guys can get an overall idea of how the internals work and adapt them to your own environments. Finally, the triggering conditions. As I already mentioned, the root file will tell us the modifications that it did. With the taint analysis, you can also determine if you find the location of the code that led to the crash, well, obviously, then you'll know the byte offset that was propagated from that original file read down to the location that it crashes at. I kind of covered a lot of this in that first slide. So yeah, just by overlaying traces and understanding whether or not the traces originate from contain the same subgraph. You can think of it this way. If the traces that lead to an exception contain the same subgraph leading up to that exception, or different exceptions contain the same subgraph at a higher point that comes from that data flow source, then it may be a cause to look into root cause analysis. And this is an important part in software development shops. When I used to work at Microsoft, obviously if we put out a point fix in a DLL, the community is very quick to point that out for us and let us know that, oh, there is this other corner case and it could go down this other path and still exploit that same bug. So root cause analysis is less of a concern for people that are trying to generate bugs for profit and more for people who are trying to defend software and secure the code that they have. And then I mentioned that we do have some plugins to other tools. We've got a console disassembler and library that allows you to utilize all of the graph analysis that we have. And a WinDebug plugin also utilizes DML. I don't know if you guys are aware of DML, but it's the debugger markup language. It's basically it's hypertext that's within the debugger output window. And when you click on it, it can execute other debugger commands. And it looks something like this. So we've just got basically the access to the call graph from within there. When you want the cross-referencing, outputs dot format, but now obviously we'll output stuff that goes back into my code. And here's an example output with the type of disassembler that you would expect from something like IDA. And the IDC is there. I hear that we're running out of time, so if you guys have any questions, we'd love to take those now. If there's no questions, you guys can reach us later via email or Twitter. And we'd like to thank Chris McBee, who was a big help on the fuzzing interface, the web distributed fuzzing.
And all the database stuff.
And all the database stuff, yes. All right, thank you very much.